25 minus 4.
All right, so we've had some time to work on this question. Thank you. So reviewing using rectangles and an infinite number of rectangles to find the area under the curve, just because I don't want you to forget this, even though we've found some other ways already. Up to this point, everybody good? Okay, so it's been up for a little while, so I'm not going to go over the details. For people who are watching this as a video, this is the first time I'm talking to you. Hello, we continue. There we go. So we have this sum here, and that sum works out to be this, and we have that in our notes earlier on, and I would give it to you on a test. Good. Then we'll expand that out and see what we get. Once we have it expanded, then, ooh, is there something else for me to pull out? Perhaps. So then I can take the limit. Oh, how come where does this 8/3 come from? Oh, is 8/3 the right answer? I can't remember. Oh, I was telling somebody that 10/3 was right. It wasn't right, maybe. I see. So 4/3. Oh yeah, 4 is equal to 12/3. Minus 4/3 is 8/3. So okay, I was just doing bad mental math. I apologize. Yeah, I waved in his direction. Anybody have any questions? Okay, then yesterday we looked at antiderivatives. And so what we did was we said our area function is the integral of the function we were given, found the antiderivative, plugged in 0 for a, because since we're going from 0 to 2, the area at 0 has to be 0. And we get a c value over here of 0. Thank you. So there's my area function. I want to know the area up to 2, so replace all the x's with 2's. And again, I get 8/3. Good. All right. On to the next page. So that page reviews the two ways that we've found so far to find the area under a curve. The first way was using this infinite sum of rectangles. So the infinite sum is the limit as n approaches infinity of the sum. So that's the blue part. The height is the f of x subscript I part, and the width is delta x. Good. So we talked about that before. And then what I've also talked about, but we haven't actually highlighted in the same way, is this notation is saying the exact same thing. It's just we discovered that rather than doing this infinite sum thing, by finding the antiderivative, we're doing an infinite sum. So this shows how these two methods are connected. Good. All right. Next, review questions. Let's do this together. Some of you did it already, but if I want to find the integral of 2x dx, what will this equal? X squared, but for full marks, plus c. Okay. Good. Then we want to find the area from 2 to 5. So what do? we start by saying f of 2 equals 0. Okay, and so we have our function 0 is equal to 2 squared plus c, and c will equal -4. Good. So then we want to find what is f of 2. So maybe I should rewrite f of x is going to be x squared minus 4. So this will be 2 squared minus, plus, what did I do? Oh, f of 5. F of 2 should be 0. That's a good thing. Oh, man. I think I should just quit, go to bed, and you can just teach yourself the rest of this lesson. Oh, man, one of those days. Whew. F of 5. There we go. That's better. 5 squared, 25. Minus 4, 21. So there we go. The area under our curve from 2 to 5 is 21. Balraj. Oh, you mean up here, this one? Yes, that should be a -4. Yes, that is a candy. Oh. Okay. Okay. Now, I'd like you to do this one. What's f of 5 minus f of 2? So f of 5 is going to be 5 squared minus 4 minus 2 squared minus 4, which equals 21 minus 0. Now, suppose I hadn't found the c value, but instead I just kept that as a c. Would it still be 21? Yeah, so it doesn't even matter what that is. It's always going to cancel out, which will save us a little bit of time and leads us to the first fundamental theorem of calculus on May 21st. Yes, but we're how far into the semester? February, March, April, May. So almost 4 months in. Okay. Here's what it says. Suppose I have this lowercase f of x. It's a function, it's continuous on this interval from a to b. In other words, no breaks, no gaps, no asymptotes, just a smooth curve. Or continuous at least, doesn't have to be a smooth curve. This integral, we would say, is the definite integral, because we have this bound from a to b. It's equal to uppercase f of b minus uppercase f of a if f of x is any antiderivative. And by any, Sharia, it means we haven't solved for a c value. Okay? So any antiderivative means we haven't found the c value. We call this, as I mentioned, the definite integral. And this is going to give us the area under the curve, between the curve and the x-axis, between a and b. So we don't have to anymore do this work here. We're not going to need it. Daniel?
So what if the integral always goes like
If A and B are numbers, then yes. Yes.
Do we need to know how to do the first part, finding C for a test?
Finding C for the test? I don't think so. Nope.
So all the yesterday works.
It was setting the stage. And you'll notice our first lesson was 10.4. Our second lesson was 9.1. Our third lesson was 10.1. And now this lesson, 11.1. So your textbook is in a different order than I think makes logical sense. So this is the order that I'm doing stuff. So a couple properties of integrals from your textbook. So just like with infinite sums, if I have some constant multiplied to the function, I can factor the constant out and then do the sum of the function, right? Okay, so that works. Or just like with an infinite sum, if I'm adding two things within a sum, I can write that as two separate sums. So hopefully that makes logical sense to you. Good. All right. So here we're going to evaluate this definite integral. Step one. What do we do with an integral? We integrate it. Find the antiderivative. So we'll say this is going to equal 1/3 x cubed plus x. But, so I'm not going to put the c on anymore because it's going to end up canceling out. I don't need it anymore, but I do need to keep track of the 3 and the 6. So what we do is we use square brackets and put the 3 and the 6 after. So notice here, the 3 to 6 boundaries are before the function. It's before we've taken the antiderivative. Here it's after the function, after we've taken the antiderivative. Okay? This is just a notation that's used by convention, so we need to get familiar with it and use it. Okay? So, reminder that this means that we will take our function when we plug in the 6, and we're going to subtract our function when we plug in the 3. So we'll have 1/3 times 6 cubed plus 6, and this will be 1/3 3 cubed plus 3. And we just evaluate. So 6 cubed, 216, divided by 3, 72. I think it's 72. Because 21 divided by 3 and then 6 divided by 3. That's what I did. Plus 6. Oh, we know I'm not always right. We already saw evidence of that today. 3 cubed? 27. And times 1/3 is 9 plus 3. Okay, you're just way ahead of me. 78 minus 12. Okay. So, for this question, this means if we were going to find the area under this curve, x squared plus 1. So, here we go. X squared plus 1. And I'm going to make it a wide-looking parabola from 3 to 6 we found that area would be 66 square units. Good? All right. Now, we've been working with x's and dx, but we could use any variable. So in this case, my independent variable will be t. So a reminder, since I have a constant multiplied to that, that's the same as 5 times the integral from 0 to 1 of e to the t dt. E to the t is the derivative of what? E to the t. But we don't need the c. Now, here's a variation in the notation. If I have just one term, as in things multiplied together, rather than doing the square brackets on both sides, sometimes we'll just do a single line, and then we'll do the 0 to 1 like that. Yep.
Would it be wrong to put square brackets?
Not wrong to use square brackets. But up here, it would be wrong not to have this and just use this as a line. So that would be wrong. Because that would tell me that I'm only going to be doing the bounds from 3 to 6 for that part. But it's not just that part, it's the whole thing. So for this one, you have to use the square brackets. Yeah. Probably. So we'll back up to what this should look like. Come down to this. Now what do I do? My goodness. Equals 5e to the 1 minus 5e to the 0. There we go. There's our exact value answer. Mahi? No, because, so the question was, could the antiderivative be 1/2 e to the t plus 1? And the answer is no, that would be undoing the power rule, which we only do if the variable's in the base. But the variable's not in the base, it's in the exponent. Sound good? All right. Next one. How do we do this? Well, we don't know how to do the antiderivative of a quotient like this. So we'll simplify it and say this is the same as the integral from 1 to 4 of root x over x plus 1 over x dx. Simplify the first term, and Mahi, here we'll use the power rule to undo it. But I left the 1 over x as it was because I remembered, oh yeah, it's not a power rule, that's going to be a natural logarithm. So when we do the antiderivative, I will add 1 to that exponent. So x to the positive half, dividing by the new exponent, divide by 1/2, same as multiplying by 2, plus natural logarithm of x. Questions up to here? Okay. Let's plug in the numbers. So you'll notice I didn't keep the absolute value signs. Why? Because the absolute value of 4 is 4. Yeah. If I had had negative numbers as my bounds, then I would have taken the absolute value. And in this case, absolute value of 4 is still 4. So where is this going to take me? 2 times the square root of 4 is 2 times 2, 4. The ln 4, I can't simplify that. Minus 2 times the square root of 1, 2. Natural logarithm of 1 is 0. Yeah. Logarithm, any base of 1 is always 0. So final answer, 2 plus ln 4. Yep.
Why is it you put like the square brackets and not like curly brackets?
Curly brackets means a set. Oh, rounded brackets? I don't know why they picked square brackets, but square brackets are just typical at this point. You could keep using square brackets there, but to switch to round brackets is fine. It's just that as long as we have this lower bound and upper bound, we use square brackets.
Either bracket, right? You want square brackets for that step.
That's right. Yep, square brackets for that step. You're ready to try some on your own?
Sure.
All right. We'll pause the video. There we go. Any mistakes in my work? Rayon? Okay. Well, 33/4. So imagine you're in your next math course and you're not allowed a calculator. So it's quite possible that university calculus, you won't be able to use a calculator. There's some courses that will let you, but there are others that won't. So practice your fraction brain. As long as it's an exact correct value, I'll accept a decimal value. Yep. You didn't have to round it. Daniel?
For your last step, right?
Uh-huh.
Are you doing cube root 8 to the 4 or 8 to the 4 and then keep rooting?
Either way, what I do is I cube root first because it's easier in my brain to get a smaller number. So that'll give me, so this turns into a 2 to the 4th, which is 16, divided by 4 is 4, times a 3 is a 12. Minus 6 gives me that 6.
How do you get a negative number in the
Okay.
How did you get a negative number in the
So this will be, so that 3 will be the same as 12 fourths. So negative 9 fourths, but I'm subtracting the negative 9 fourths, so I end up adding it on. Shh. Brian. Okay, so as long as I have the integral sign, I have the dx. Integral sign, dx. No integral sign here, so no dx. Because I already found the antiderivative. Shh. Hey, stop talking. So I've already done the infinite sum. So it's kind of like if we look back at this question, between here, try that again, between here and there, I lose my summation notation because I've already done the sum. So the dx is part of the, it disappears when we do the antiderivative. Yep. 9 is good. Who wants more time for number 10? Not very many people, so let's just go over it so we get to our next example. There's my work. Yes. Okay. And Rayon, getting back to your question, this is an exact value answer. So if we plug it into our calculator, because it's irrational, we end up rounding off. So if you're not asked to round, then give the exact value. Yep. Yes. Ready for the last example? All right. We want to use fundamental theorem of calculus, which is what we've been practicing today, the definite integral, to find the area under this curve and above the x-axis. Daniel, you have a question?
Your right bound goes on top of the bounds, right?
That's right. Left bound is on the bottom, right bound is on the top. There are times that those numbers are in the opposite order, but we'll see that, and we just go with the flow. So what are my bounds for this? How do we know? Oh, yeah. So we want to know where this is above the x-axis. We need to know where it intersects with the x-axis. So we want to solve when 0 is equal to 4x squared minus x to the 4th. And yes, we can solve this by factoring. Good? With this much information and with your brilliant understanding of Math 30-1, you could sketch a graph of this. Multiplicity and behavior. Yeah, well, why don't you sketch a graph?
Give me room.
So you want to find that area. So we'll do the integral of 4x squared minus x to the fourth dx. Reminder, you have to have those brackets. And the bounds. Well, it was suggested we go from -2 to 0, and then 0 to 2. But if I just went from -2 to +2, because my graph doesn't go below the x-axis in between there, I can just use these as my boundaries, since it just touches at 0. If it went under, then what happens is the area that's underneath turns into negative area, and then it gets subtracted from the area that's above. We'll talk about that more in tomorrow's lesson. So with this much, I will let you finish off the question. Sounds like some of you are getting the same answer. Yes? Excellent. There we go. Thus ends the lesson.